So welcome back to Chemistry 20A. It's still a chemistry course. I know the title is a little bit odd, but this lecture, we're trying to talk about some of the very, very basic math and physics we're going to use for this class. So if you took AP Physics or AP Calculus, it's going to sound like a review for you. But I hope this lecture can prepare everybody equally well for the material we will be covering in the following lectures, which is very basic quantum mechanics. All right. So before we get started, I have two little reminders I want you to pay attention to. The first one is I do want you to check your Cengage assignment, which is the online assignment platform. So on your Canvas side, click on that Do This First. That's going to register you for the Cengage assignment, and then just try one or two assignments on there and make sure the platform is working for you correctly. If you have any problem, I think now is the best time to contact them for technical difficulties. All right, so first thing, check your Cengage assignment, make sure it is working. Don't wait until the night before submission. And then I also posted a syllabus survey or a syllabus quiz that worth 5 extra credits that is due this Sunday. So do go back and try to do that syllabus quiz and read the syllabus, get to know what is covered in this class and what my expectation is. Okay, so that's the administrative part. So today we'll be talking about basic math and basic physics. So the reason we're doing that is because eventually we'll be talking about quantum mechanics, and to do that you'll need an understanding basic calculus. And also some of the fundamental things when we're talking about in physics, like what is a wave, what is potential energy, what is kinetic energy. All right, so this is a preparation for our quantum mechanics course coming up. Okay, first part, derivative and integral. So again, first thing first, this is still a chemistry course. So we will be only focused on the application and physical meaning, not mathematical details. I'll show you some example later on, but the bottom line here is I'm not going to ask you to solve any very complicated integral or derivative. It defeats the purpose, but you do need to understand what I'm saying when I'm talking about a derivative. All right, so for example, when we're saying derivative, that describes the rate of change of a function at a given time. We'll see an example, but one of the typical applications we're talking about derivative in physics, if you think about the velocity, right? So that is the change. So we use little d to say that's a change in distance over change in time. So that's when we're talking about derivative. Our first derivative describes how fast a property changes with respect to a second dependence. We'll occasionally also talk about second derivative. So it's a little bit odd when you're talking about second derivative. It's more like the rate of the rate change or the derivative of a derivative. So again, in our real lives, the best representation for a second derivative is acceleration. So acceleration describes how velocity change as a function of time. Which, if you think about distance, that's a second derivative. Over time. All right, so these are just very fundamental. What exactly we're talking about when we're saying derivative? It's not mysterious. It's just talking about the rate of change. So going to one of the examples, it's the simplest example I can think about. It's more or less a linear regression. Or if you think about, not linear regression, sorry, a linear function. So on the left-hand side, let's just define y, which is a function of x, or fx, equals to mx plus b. So that's why you have this linear plot here. So that means the property y depends on a second property x. So on the y-axis, that's where this equation shows. So that's equals to fx equals to mx plus b. So when we're talking about derivative, again, what we're trying to say here is how exactly is the rate is changing. We're talking about the rate of change for this equation here. So the other way to put it is if we know x is changing from x to x plus delta x. So say we start from here, right? So that's x plus delta x. Likewise, on this equation, we have y and y plus delta y. So the question we're trying to answer here is how is delta y related to delta x in this relationship? So it's going to be quite simple here. Let's just write it out. Say y plus delta y, that's on this point here. Or let me use a different color. That equals to m, which is a slope, times x plus delta x plus b. And also we know here y, by definition, y equals to mx plus b. And write out the term. We have mx plus b plus delta y equals to mx plus m delta x plus b. And now it becomes quite obvious. We can cancel out some of the terms here. Mx also cancels out. So what we end up is a simple relationship between delta y and delta x. So delta y equals to m times delta x. So this is the simplest example in how do you actually solve a derivative for a mathematical function. So in this case, we can say we solved the derivative of fx equals to mx plus b. What it means is we can write dfx over dx. So this means the derivative of fx with respect to x equals to d dx mx plus b equals to m. So the derivative of my linear relationship is just a constant number, that is the slope. So taking this a little bit further, if you think about it, what is the second derivative of this linear relationship? Care to make a guess? Yeah. Zero. Yeah, so it is just zero, right? So the rate of change in this linear relationship, that is a constant. So the rate of that rate of change is just going to be zero. So the second derivative for the linear relationship is zero. So, I mean, I probably will never ask you to solve this derivative in this class, but you need to know how that comes from, right? When you're reading the derivative table, you need to know what that actually means. So that's the basic of derivative. Question before we move on? Okay, we're all smart here. Right? Calculus is not that hard. And okay, that's the derivative. Now we're moving to integral. So integral, we have different ways to introduce it. So here I'm just going to use one of these approaches, which you can imagine integral in a way we're trying to solve what is the area under some kind of curve. Again, if you think about mathematical function, that's the same idea. So we always start from the simple case. So if my function of interest is just a straight line, it's just a constant, so fx equals to a. It doesn't have any dependency on x. So this area here, which is also highlighted in blue on the left-hand side, between x1 and x2 is just equals to height times base. And apparently this is A, so that's just A times x2 minus x1. Simple and nice and easy. And then when we're taking one step further, now instead of having a completely constant, now we have, again, a linear relationship. So my y equals to mx plus b. And on the bottom, likewise, we have it from x1 to x2. So fx equals to mx plus b. So this area 2 here, again, equals to average height times base. Right, so the height here at x1 and xb are no longer equal, so we're taking the average of these two heights and then times base. That's going to give us 1/2 times mx1 plus b plus mx2 plus b. So here we're talking about the average height. And that times base, x2 minus x1. And then we write it out. We have 1/2 mx2 prime square plus bx2 minus 1/2 mx1 square plus bx1. Still not too complicated, a little bit more complicated than what we talked about before. So when you have a more linear relationship, you're talking about the average height and times the base. So now we're moving on to the actual application of integral. So now imagine that fx is a random curve. We don't have the mathematical representation here, just some kind of the curve. So how can we find the area below this curve here? Again, in this case, what we did is just imagine you put very, very small distance here between each step. So we're defining the height of the i's rectangular to be fxi. So in this case, because the rectangular is like really small, the difference in these becomes the actual area here becomes a good estimate about how much area is below the curve there. So we're just using it as an estimate in what that little part is under the curve. And if we write down the area, again, that's going to be roughly equal to height 1 times base 1 plus height 2 times base 2 and all the way to xn. So it depends on how much steps we're taking. So for each step, what we can estimate it to be fx1 being my height 1 times delta x plus fx2 times delta x and all the way through. Or you can write it as a sum. For I numbers, we have fxi times delta x. So in this example, what we have is when my delta x is smaller, we get better approximation. Of the curve. So this is also easy to understand, right? So if you imagine I only have 2 delta x, then this becomes a very bad representation about the area below the curve. But if I have more of these delta x steps, the estimation of that area under the curve just becomes better and better. Or if we put it more strictly speaking, it's when delta x approaches 0, we now have a definite integral. Right, so what we're having is the area under the curve is from x1 to x2. We call it definite integral because we know what exactly we're talking about. We're talking about the region between x1 and x2 and fx dx. Right. So that's the idea of integral. We're just trying to get an idea. We're just trying to use integral as a tool to estimate what is the area below some kind of curve. So that's derivative and integral. And here I want to show you one of the example. It's like what I expect you to use these tools in my class, in the chemistry class. Okay, I'm just going to put the document camera on so you can go back to the problem while we're working on it. Let's see. If your calculus is good enough, you don't even need to use a magic calculus. I just provide it there. All right, so let's read the question together. So here, just given the probability of finding a ground state pi electron in this molecule called 1,3-butadiene at position x, we can estimate it to be px equals to 2 over L sine square n pi x over L. So in this case, we'll go over them later, but n equals to 1 means it is a ground state. And then we give the length of this butadiene molecule, L, equals to 4.22 angstrom. So, by quantum mechanics, we know that the total probability of finding the electron from 0 to x1 can be given using the integral here, which what we're doing is a probability, right? It's a probability curve. What we're doing is taking the integral from 0 to x1, and that integral over the probability curve gives you the total probability of finding the electron in that region. So it's the same idea. You can imagine this as a probability curve. And the area below it gives you the probability of finding that electron somewhere along that line. And I will always be giving you the magic calculus because I don't expect you to solve these calculus problems in my class. So if your calculus is good, you can use your calculus. If you don't know how to use it, you can just plug in the numbers using the magic calculus provided. And one of the typical questions I could be asking is, what is the probability of finding the electron from 0 to 1.34 angstrom? So this is what I want you to do, is read the question and know where and when and where to plug in the correct number. So what we have here, let's just work on it together. I'm just going to copy paste down my magic calculus and get an idea about what that means. So here, in this equation, what we have is px that equals to 2 over L sine square n pi x over L. All right, so what we're doing, that is the px. We're integrating my probability function in a certain area. So we're finding the probability. And that is what the question is asking for. And in here, we have some of the information that we already know, right? So n equals to 1. So that is given here. And then L equals to 4.22 angstrom. And then writing the actual integral down, because the question is asking for the probability of finding the electron from 0 to 1.34 angstrom. What that means is if we write it down, we'll have x equals to 0 to x equals to 1.34 angstrom. What we're integrating against is px dx. So in this case, because we have the magic calculus, we can just plug in the numbers. So first we look at the top one, right? So that's the 1.34. So that's 2 over L times 1.34, which is the x here, over 2 minus 4.22 over 4 pi times sine 2 pi times 1.34 over 4.22. All right, so this part, we're calculating the top part. And this is gonna, then we can calculate the bottom part, x equals to 0. Same idea, right? 2.L times 0 minus 4.22 over 4 pi sine 0, which is also gives you 0, but I'm just writing everything down. And then you can do the calculation. Right now, we only have numbers here, right? So L is a number. Okay, sorry, that's 4.22. Let me just write it in. And now you're ready to plug in that equation into your calculator. That's actually going to give you a real number, which in this case, it's going to be about 0.172 or 17.2%. So that means, going back to the physical meaning of what we're actually solving here, we have an equation that represents the probability of finding the particle somewhere in that 0 to 4.22 box. And by solving the integral here, what we're getting is, imagine you have this curve, this probability curve, right? And the total length is 0 to 4.22. But the probability of finding this electron somewhere between 0 to 1.34 is about 17.2%. All right, so that's the physical meaning of the mathematical equation we're solving here. Again, I'm just going to write it down. So don't be afraid of calculus, of seeing these integrals and derivatives. They're just there to help you understand. Okay, yes?
Do you have to take into account that L is 4.22 angstrom?
Yes, so here is the thing. What we have is that in this equation, what you didn't see is we're also integrating against x. So everything is in angstrom. So x is also in angstrom. So what that means is, if I give you the question, say finding the probability of the electron from, say, 0 to 1.34 times 10 to the, say, -8, and then you want to translate that meter into angstrom. So you need to keep the unit consistent when we're doing the integral and also the derivative. And that's a very good question. Any other questions before we move? Yes?
Why did you round some numbers to 0?
Why do I round some numbers to 0? So I did not round some number to 0. So in this case, it's just because the question is asking for the electron from 0 to 1.34. What that means is, in my integral, I'm actually doing my integral from 0 to 1.34. All right, so the upper bound here is 1.34. The lower bound here is x equals to 0. So what I write here is actually this x equals to 2 term. And when x equals to 0, and this x equals to 2 term also equals to 0. Or x equals to 2 equals to 0 when x equals to 0. Right, likewise, in the sine term, we have sine 0, because sine 2 pi x over L equals to 0 when x equals to 0. So it's not like I just throw out the term. It's because we're rounding it from 0 to 1.34. You could easily imagine, say, if I change the question here, instead of 0, we have 1.00 angstrom to 1.34 angstrom. Then instead of having 0, you'll have to plug in x equals to 1.00 here. Yes?
Yeah, sorry, what meaning does the A have in this case?
Angstrom is just a unit we normally use when we're talking about distance in atomic level. So that basically means 1 angstrom is 10 to the negative 10 meter.
Are we supposed to know that information from each reference?
This doesn't really matter in this case because we're getting the probability at the end and the angstrom will cancel out. But if there is a unit conversion problem, I'll give you that information. Okay. So that's the very, very basic derivative and integral and basic calculus we're going to use for this course. All right, so nothing more complicated than that. So don't be afraid when you see that again. And we're ready to move on to a little bit more physics here. Okay, so switching gear from math to physics, now you know basics of calculus. And I want to teach you a little bit of basics of physics, and these are the concepts we will be using in the following classes. Starting from wave. So waves are by definition, they're just oscillating functions with crests and troughs at certain instant at time. So this is a typical example of a traveling wave. So here what I mean is crest and troughs. So here are some of the terminology I would like to use when we're describing wave in this class. And these I do expect you to know what they mean. For example, when we're describing wave, there are several properties of a wave we can be talking about. The first one is called amplitude, or sometimes abbreviated as a bigger A. By definition, amplitude means the maximum displacement of the surface compared with the undisturbed one. So that means if we took the distance from the peak to the reference point, so that's going to be my amplitude. Likewise, it's going to be the same if we take it from the trough. All right, so that's what amplitude means. And in this case, since on the x-axis that's distance, on the y-axis that's phase, so if you imagine an oscillating wave, the unit for both x and y-axis are meters. So in this case, the unit for amplitude is also meter. Well, at least in the example shown here. Next up, now we have the vertical part, right? So how big my wave is, what is amplitude of my wave. Next property we use to describe a wave is called wavelength. So that's by definition the distance between two successive crests or troughs. So in this case, we'll just use the crest as an example. Right, so the distance here, that's wavelength. The other way to think about wavelengths is a lambda wavelength equals to distance per cycle. Right, so how much distance the wave is traveling in one cycle. This also has a unit in meter. The next one is a little bit more dynamic, it's called frequency. So now frequency, that's the number of peaks that pass a given point per second. So this one I do need to draw two different figures just to show you what it looks like. So imagine we have two waves that are traveling at the same velocity in the same time period. And a low frequency wave would look something like this. My drawing is not ideal, but you get a gesture. Right, so in that certain time period, only 1.5 of my low frequency wave reach the point. Alternatively, we could also have high frequency wave. So something like that. You know, my drawing is really bad. The annotated note has a better version of my drawing. But this is a high frequency wave. So if you look at the top one, we have roughly 1.5 entire wavelengths pass by. And on the bottom, we have 1, 2, 3, 3.5 lambda passed by in that certain period of time. Or the other way to think about frequency, or the Greek letter nu, that gives you cycles per time. So number of cycles over time. All right. And note that when we're talking about frequency, wavelength, amplitude, these are all like independent properties when we're talking about the wave. And at the end, we have the speed, or the distance that's traveled divided by the time elapsed. It's the same idea of defining any speed. So we have velocity, speed equals to distance over time. And for waves, remember we talked about before that wavelength is distance per cycle. All right, so that's my wavelength. And if we got the cycles on the top, cycle per time, and this is my frequency. So this comes to the conclusion here is the velocity of a wave also equals to lambda wavelength times frequency. So everything here is rooted back into the definition of wavelength, frequency, and speed. And that's connected to light wave. So remember last class, we talked about the universal constant. So the speed of light, or in general electromagnetic radiation, including X-ray, UV light, or visible light, and gamma ray, and all the electromagnetic waves. The speed of electromagnetic radiation in vacuum, that's our universal constant. By say constant, it remains the same. So what that means is that C equals to lambda times mu for all EM radiations. Or just light. Sometimes I'll use light and EM radiations to convert them with each other. So this is more or less an intuitive idea when we're talking about wavelengths and frequency of a light. So if we look at the EM radiation spectrum here, right, we know the product of wavelength and frequency is a constant. So that means if we have higher frequency, lower frequency here, if we have lower frequency, we expect it to have longer wavelengths. And likewise, if we have higher frequency, we expect it to have smaller wavelengths. So that is the intuitive idea you should be getting, right? So what's the relationship between frequency and wavelengths when we're talking about electromagnetic wave? So here's one of the example questions. We can work on it together. Can you calculate the frequency of an ultraviolet light with a wavelength of 335 nanometer. You'll see this probably as a part of your bigger problem, but you need to know how to interconvert them. So the equation we'll be using is C equals to lambda times mu. Or this question is asking for the frequency given the wavelength. So what we have is frequency equals to speed of light divided by lambda. And plugging the numbers, the speed of light is roughly 3.00 times 10 to the 8th meter per second over 335 nanometer. And we know 1 nanometer is 10 to the -9. And plug in the numbers, you get 8.96 times 10 to the 14 S minus. Or we can also write S minus as hertz. So these two units are equivalent to each other. That's the unit for frequency. Okay. And before we move on, I do want to quickly mention another type of wave. So far we're talking about traveling wave. So I'm speaking, my sound wave is passing throughout the room, so that's a traveling wave. Another example is like a standing wave. So you can also imagine like a guitar string where both ends are fixed, and then you play it and you see the guitar string moving up and down. Because both ends are fixed, we call it a standing wave. So different from traveling wave, standing wave has some limitation on its wavelength, right? So both ends are fixed, so the wavelengths have some limitation. What that means is the integral number of half wavelengths must fit in to the length of the string. So let's say the length here is L, and then what is the wavelength? What is the wavelength of my first wave, or my first harmonic wave here? This one, the length is L. And care to take a guess, anyone? Yes. Yes, so my first one is lambda equals to 2L. That's my first harmonic. And then for the second harmonic, we have lambda equals to L. And for my third harmonic, we have lambda equals to, let's see, 1, 2, so 3. Or the other way to put it in a more general way is n times lambda over 2 equals to L, where n can take any integer number here. And on this figure, I'll just remove some of these numbers. We also have another concept called node. So what that means is in my standing wave, whenever you're, well, in wave in general, whenever you have a point where the wave actually has a number of 0. So here if we take this to be x, this to be my y, we start from 0, and whenever my y equals to 0, that corresponds to a node in my wave. So in this example, in my first harmonic, there's 0 node. For my second harmonic, that's 1 node, and this one has 2 nodes. All right, so these materials, they're not hard, they're just a little bit of terminology. Yes? N just means any integral number. So right now we're showing like n equals to 1, 2, and 3, but you can imagine that goes more like 1, 2, 3, 4, 5, 6. So any integer number will be your n. Okay. I do have an example question here, but I think I'm running short on time. So take your time to try this example question. You will be able to see the answer in the annotated note as well. Okay. All right. So before we finish, we have 10 more minutes. I want to very quickly talk about energy in classical physics. So before we move into quantum mechanics, need to know at least something about what is classical theory, and then we can talk about what is wrong with the classical theory. So in this case, when we're looking at energy in classical theory, naturally, we divide it into kinetic energy. So that is the energy of any moving object, 1/2 mv squared, where v is the speed. So imagine you have a car going, right? So that's the kinetic energy in that moving object. Alternatively, we can also have potential energy, which is the energy stored in an object due to its position relative to a reference point. And I think we all see this example quick, right? You have a pen, you drop it. And the reason it is dropping because at this position, it has potential energy stored in it. So that's a classical idea of energy. This part is actually generally applicable, but we'll talk about the quantum mechanical picture of kinetic energy and potential energy later on. So let's look at an example called the classical harmonic oscillator. So harmonic oscillator, as you can imagine here, we have a ball that has a mass of m. It is attached to a spring with stiffness K. We're ignoring gravity in this case. And it's being placed at the equilibrium position x0, and it is perfectly happy there. It does not want to move unless something changes. Right, so that's the beginning point. And now you can imagine two different things taking place. One of the things is now we're stretching this ball. We're stretching the spring, makes the spring longer. Move this ball from x0 to x1, where x1 is larger than x0, or in the other way, x1 minus x0 is a positive number. So what is the restoring force for that hypothetical spring? That's going to be going back, right, leaning towards the reference point. Or we can write the direction of the force here. Or due to Hooke's law, we can actually write down an expression of F equals to negative K x minus x0. And this is a negative number. Alternatively, you can also imagine a different scenario where you're compressing the ball, where you're compressing the spring by moving the ball to the left-hand side to a different position, say x2. And x2 is a smaller number comparing to x0, or x2 minus x0 is a negative number. So now again, your ball, because the spring is being compressed, it has some kind of energy, potential energy, wants to go back to its original position. So we'll have F equals, well, F going to that right direction. And again, due to Hooke's law, F equals to negative K x2 minus x0, and that's a positive number. So that's, we're talking about force. And translating force into potential energy, what we have is Ux equals to, well, so before we go there, we have the force by definition equals to negative du over dx. So in this case, what we have is the potential energy equals to 1/2 K x minus x0 squared. So again, we have the direction of the force, and we have the potential energy surface here. Well, what is my the point I'm trying to make here is if you look at this potential energy diagram, I'm not going to ask you to derive it, but the bottom line here is this is a continuous diagram. What it means by continuous, that means imagine that ball and the spring. You can put that ball at any position at that spring, wherever you like. Your x can take any arbitrary number, and at that any arbitrary number, you will have a potential energy associated with its position. Right? So in the classical physics, in my classical harmonic oscillator, what we have is a continuous energy relationship. Or, if we draw it out in classical theory, the energy is continuous. So let me just highlight it. What it means, so this is what I call an energy diagram. So in my classical oscillator, so my energy can take any value it like, or at any point x, E, or in this case, we're talking about potential energy only, can take any arbitrary number. All right, so the way to read it, this is the energy diagram. The whole point here is, say, in the classical oscillator, you can put that ball at anywhere you like. And at anywhere, you will have a corresponding potential energy associated with that position. But in Friday, we'll quickly see, in some cases, classical theory actually doesn't work, and we need some kind of amendment. Well, people thought they need some kind of amendment to make the classical theory work. But at the end, what we find out is these classical theory just simply is not true when you're looking at very small systems. And that's the birth of quantum mechanics. So on Friday, we'll see how is the Max Planck's quantum hypothesis comes to play when we're trying to explain the black body radiation. All right, thank you everybody for your attention. I'll post